Okay, so we're back at it. Today, what my goal is for today is to so we've basically implemented these I don't know, it's a bit too light. I think that's about right. It's probably the window. We don't like the light. We don't like the daylight. So yeah, too many lights at once. Anyway, we've got these two pieces implemented. So what I want to try today, before we move ahead and understand anything else, is I want to do to make sure we solidify our understanding on about this kind of stuff. Is I want to essentially do sort of take an actual input, right? Because again, this is the input embedding. Then you get the output probabilities. So anyway, I want to take a look at the input. I'm not so sure. I'm not so sure that this architecture here is. Yeah, no, that's the thing. That's the model, right? So the thing is, what is it that you're going to be training? Like, I think what you're going to be training, because I had the feeling these got some sort of like. No, but that's not, you're not really training that. You're just calculating those things based on similarities and all this kind of stuff. The training actually happens here. This is the blue boxes is what you're training, the feed-forward networks. This is what you're training. So what I want to do today is I want to basically get an actual working example of, getting an actual English sentence as an input, and then starting sort of taking a look at the different matrix representations and whether we understand, whether these things make sense or not. And even kind of see, just start from a very naive case and do, for example, like just a very naive modeling. So just a kind of like a one dimension per token or something like that. And then see whether whether these things make sense, whether these things work well at all. Because we really haven't checked the code in detail, right? So we're kind of trusting that Ghostwriter gave us something that makes sense here. But let's start with these. So we now I now want to do some sort of end-to-end test, as in I want to start off with an English sentence, something short and simple. And then test the process of passing it through the positional encoding, and the multi-head attention mechanism. I want these to be easy to understand. So we probably can start with very low dimensionality, so that it's easier to visualize as well. Let's see. Now, hello world is sentences. Hello world is too simple. Okay, but we've got an explanation. Sure, we can use a simple input sentence to test the positional encoding and the multi-head attention mechanism. Here's an example. Define some hyperparameters. Okay, but D model 8, we're starting already with yeah, okay, it's not 500, but it's quite some stuff. Number heads, max length. Tokenize the input sequence. So let's do this. Can we have a slightly more complex sentence? Something that's grammatically more real. Is it really gonna use a fucking brown box? The quick brown fox jumps over the lazy duck. Yeah, that's quite a standard one in computer science, right? Yeah, but it's why not? Let's see, right? So there's some adjectives and some some verbs. So cool. Let's go and copy that. So I'd like to have this stuff a bit organized so that that thing doesn't grow too much. Can we have how can I have that in a separate file? Okay, I want to have the attention and encoding in a separate file. So the attention and encoding bits in a separate file, and the testing code in the main one. So I got less scrolling to do. How can I do it? So I probably want to have attention. Okay, so let's do that. So attention Python. I don't know if that's going to be if that's going to be something that will stay like that later on. So we've got attention Python. Cool, no testing code in here. Attention Python, and in the main file from attention, I guess that works. Does this work like that? I guess so. I can just let's see. So and then attention pi is this stuff. Okay, I don't need to actually specify anything like export or anything like that. So let's see. So let's go and did I copy that already into main py? Yeah. So what does it do? Oh, wait a second. Why is now? Oh, yeah, 16. Okay. It's funny because it's increased the dimensionality, I guess, because this is a bit more complicated. But what happens if I lower it down? Let's see if that's something that we can at all like read and work with. So we have some hyperparameters, and then we have a sentence. The quick brown fox jumps over the lazy dog. So we tokenize the input sequence, and what do we do that? We split tokens. So let's see how that looks like. Pre-tokens. Well, let's. You know what? Can you add some debugging prints for main pi? This is amazing. Like, this is what I like about this, because it just no, but it didn't do it. Okay, output attention, and also add some prints for the tokens. Yeah, exactly. So we've got these now. So the quick is the stuff. Then we have the tokens, and we print the input tokens. Then we convert the tokens to padded one-hot vectors. Convert into NumPy arrays. Create the positional encoding. So this is the positional encoding, and then apply the positional encoding to the input tensor. And then you create the multi-head attention layer. And so what are we printing here? We're print the initial input tensor and positional encoding output. Initial tensor shape position. That's the problem, is that we're printing the shape, but we're not really. What I want to see is I want to see the encoding better, right? So I'm thinking I might actually just force the dimensions to be less, so that we can at least go through these weights and understand what's going on. Print the output and attention weights. Apply the multi-head attention. I'm trying to go as low level as possible, so I understand. Just I can understand kind of in a more of a first principle kind of way, like whether this encoding really makes sense, right? See it in action. Print the output of attention, the output and attention weights. Input sentence, one hot encoding. Let's see first, does this work at all? No. Okay, cool. So let's see. Operands could not be broadcast together with shapes. So this is in okay, but it's essentially it's split. It's decided to split the sentence in tokens. It's interesting that it's using the dot as well here, right? So dot. The full stop is part of that token. It kind of makes sense as well, right? Because it adds meaning to this, positional meaning to this word. Okay, so now how do we debug this? So code error detected, debug with Ghostwriter. Let's try these. Oh, that's cool actually. Oh, that's very cool. Okay, so actually I hit that button and it's helping me debug that. So okay, that is cool. So it says the error is caused by difference in shapes of the input tensor and the positional encodings tensor, specifically X shape. To fix this error, you need to broadcast the positional encodings tensor to have the same shape as the input tensor. To do this, you can modify the call method to broadcast the positional encodings tensor before adding it to the input tensor. It's actually pretty crazy. So the error is caused by the difference in shapes of the input tensor and the positional encodings tensor. Specifically, X has a specific shape, right? I'm not sure about this batch size, but yeah, whatever. Because it seems to be just we're using 0 right now, or just one batch, while has a shape of one max length D model. To fix this error, you need to broadcast. But actually, the thing is max length 1620, whatever it is. So it's just the and how does it look like now? Look at the call method. Versus what is it? Fix the broadcast shape here, but isn't that code the same? Ghostwriter, you need to replace line 12 in main dot. Oh, so the fix is on main dot, on the main file, not on the attention file. Because that is the same, and that is exactly, and that is fine, that is correct. With these. Okay. There's something a bit uneasy with these, as in like you kind of have to learn to let go of some of these details, because it's just like at the end of the day these are low-level details that of course you feel like you should know and should be in control of why things are, but at the same time they would slow you down so much, right? Let's see if that Ghostwriter helped us there. So tuple index out of range. I like the button, actually. It helps a lot because you don't have to think about the you don't have to think about you don't have to think about the how would you type you know, how would you type that, and actually types it for you. And it's funny to see that now it's like there is on line 31 and oh, sorry, actually I replaced it in the wrong place. Oh no, but it's fine. Ghostwriter replace line 12 in main.py with, but that's not line 12. That's the thing, right? Line 12 is just a comment. So I assume that's what they meant, and now they are like, you're trying to call P, but P is expected 2D umpire, right? Specifically P expects an input tensor with shape. Something tells me that's gonna get me into trouble. Let's see. Together. Line 19. Yeah, it's getting these lines wrong, and it keeps referencing these line, and keeps. This is a bit funky, but I mean, I wanna. So, X essentially. What else did we print X? Maybe we need to use our brain a little bit as well. Print X. And then we'll run this. See if now it works. This doesn't work. But X essentially is an array. Convert the input IDs to an umpire array. To pattern one hot vectors. Append. So what is this stuff here? So print one hot vector, and then we add this stuff, which is what we just did. It's just one thing, but it's just vector, and then it just appends it in there. Okay. I'm not so sure I understand what is this, but that's what makes it difficult, right? Because we don't understand really, like the code is generated for us, so it's super hard to understand what is it that it's doing. But I think that effort actually will pay off. So. What do we have here? So could not be crossed together with shapes 121 2016. He tokenized the input, convert those into palette one hot vectors. I have the feeling there's then somehow like a mismatch between the padding, this one hot vector. So what are the padded hot one hot vector? I have the feeling that this is kind of what's not working well. Because then we need to apply the position encoding into the input. So again, what we're trying to do here, maybe it will help if we reduce the D model, the dimension of the model to be 1. Okay, so what happens now? T model is 1, right? Okay, because now it seems like now it's working, right? And now it's failing in the multi-head attention step. Input tokens. Let's stop here for a second. Or can we just say can we just transform code, comment out. I mean, that would be okay, cool. Replace selection. If it was a little faster, that would be actually pretty cool. And then if I do this and then it's like, can I do transform code, remove comments? Like, is it gonna work? This is so good. Like, this is so useful. I wish it was a little faster though for this kind of stuff. I know you should have like a shortcuts and stuff, but you don't need to think about this stuff. That's awesome. Look at this. It's awesome because it actually keeps the original comments. It's really nice. It was valuable, but I'm not going to use it. Thank you. Let's do though the print. Let's print X. Okay. Let's print X. So we just have now, so remember, we have just a model that is dimension 1. So what we're saying is we're going to represent each token with just one number, because that's what we wanted to do with the positional encoding, is that we want to represent each token with a vector or an array of numbers of like D model dimension. And then the positional encoding was essentially what was doing. It was padding this. It was kind of adding stuff on top of it, based off of what? It was adding something with the sine and cosine. Like it was adding, yeah, it was adding stuff to the positional encodings. And these were supposed to basically encode things like the relevant in the position, the sort of encode more things in there, right? Encode the relevance, like kind of the position, so to say, right? So to make sure that a word that if the same word is at the beginning or the same, and then the same word is at the end of the sentence, that they don't get the same representation, because that's a mistake. We want them to be different, right? And I guess this tokenization here, no, this is where we're having a little problem. And that's, I guess, what converts the tokens into the actual vectors, which these should be, I don't know exactly what's the best way to do that, because my assumption is this is where some domain knowledge should go in, shouldn't it? Like how you actually encode the stuff. But let's see if that runs at least. Boof. Okay, so we have big matrix now. Why? Input IDs. Max length 20. So has it replaced actually each token, like 1, 2, 3, 4, 5, 6, 7, 8, 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. For sure. No, there's a lot of data in here. Why so many? So what is let's first try to understand these. So explain code. This code takes in a list of tokens, and it then creates a list of one-hot vectors for each a list of one-hot vectors for each token. Padded with zeros to the maximum length. Okay. It then appends each one hot vector to the input IDs list. Yeah, that's the explaining. So why do we need these? Let's why do we need the padded one hot vectors? Let's ask. So why do we need the padded one hot vectors at all? The padded one hot vectors are used to represent the input sequence. In natural language processing tasks such as the one in code where we tokenize a sentence, the input sentence can have variable length. However, in order to apply neural network models to these sentences, we need to have input tenses with fixed shapes. So I guess what this means is if max length is 20, 1, 2, 3, 4, 5, 6, 7, 8, 9. That's 9, right? So max length is like, this tells us how long of a sentence can we process. So if I lower this to 10, and that's what it's doing. So that's what it's doing here. Okay, that makes it easier to read. Perfect. But it means we can process longer sentences than these, right? I think. A common approach to overcome this problem is to pad the input sentences with some token, a space character, to ensure that all sentences have the same length. One hot encoding is a way to convert words into input sequence into numerical vectors, where each vector has a length equal to convert words in the input sequence. So into numerical vectors. So each vector has a length equal to the size of the vocabulary, and only one element of the vector is set to 1 at the index corresponding to the word in the vocabulary. Combining these concepts, we can pad the input sentences with a special padding token and then convert these padded sequences into one hot vectors model as input. So this is just a way to do it. But so essentially what this is doing is, so we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So we have 10. So we have these like 10 values. But why do we have 5, 6, 7, 8, 9, 10? Why do we have 10? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Is it essentially the size input tokens? Print and tokens. Tokens. Oh, but that does it for. So I guess token 0. It's 9 words. So am I just being dumb? So why is it? So in why is it generating a 10 by 10? So in the code, max length is set to 10. So when creating the padded one, make sure that each one hot vector is length with max length, especially exactly. And painted one each tokenized sentence. This has the length of the longest sentence in the input 10. The shape of the resulting array 1, 10, 100, where 1 is the batch size, 10 is the length of the padded sequence, and 100 is the length of the one hot encoding. 100. So that's map to a word. I'm getting dizzy. Each element of the 10 element array does not map the vector word. It rather each element in the array corresponds to a position within the padded sequence. Each element in the input sequence can correspond. So can you, how these encoding maps with the input tokens? So here's an example. So say, okay, so we have, so you have the so tokens, and we create each padded one-hot vector. We first convert each word to a list of integer Unicode code points, and then concatenate them to form a single list. Each sequence of the integer codes is padded with zeros to reach the maximum length of 10. So the resulting input IDs will look like these. Yeah, exactly. Okay. What? So 1, 2, 3, 4, 5. Wait. So we first convert each word to a list of code points. What are these code points? And we concatenate them to form a single list. Each sequence of integer codes, I guess each sequence, right, is padded with zeros to reach the maximum length of 10. Yeah, that's how you might, exactly. The resulting input IDs will look like that. So this input IDs array is then converted to a NumPy array. Fine. To map the one-hot vectors back to the original words, we need to reverse the process of converting each word to a list of code points and concatenate the code points into a single string. Okay, so what it's doing here is it's taking, so it's iterating over, as an example, it's iterating over the first one, right? So it's iterating over input IDs. No, it's iterating over the whole thing here, right? No, it's iterating input IDs, yeah, 0. It's iterating over each of these. That's not, that makes no sense because, let me try that. Can I try that? Let's comment that as well. Comment out, and I'll have to drop. But that's a good exercise. So we're trying to understand really step by step what's actually happening in the code. So how are we transforming this stuff? So and actually missed these two, but it's fine. So we want to add this test code here now. Let's see what it outputs. It's correct. The quick input IDs. So what it's doing is prettier. Can I do that? To list. No. That's fine. That's fine. We'll have to get to live with this, but I have to leave in a minute, so that's all good. So if I print the 0 stuff, essentially, I'm just printing a whole thing. But then I don't understand, how is this structured? Am I just stupid at reading tensors or arrays? Oh no, it's one single thing, okay. I think this might have misled me, these input IDs. This is each, one of these is like each sentence, is it? No. I think so, it's actually test sentence. If I do that, what is gonna happen? Now I have two, because I have 2 sentences. Okay, cool. So so that's each sentence in the input, and that's kind of then defining the batch. So okay, so that's the full sentence. Okay, so it's the full sentence encoded. So what it's doing is it's stopping where there's the first 0, right? Because that's then the kind of the padding code. Okay, so essentially it's nothing else than it's just taken the Carter representation. That's it. Print S. But why isn't it printing longer? Range 10? Oh, okay, I can just range 30. And I'll leave it here, guys. Yeah, okay. So it's actually recovering the... So it's essentially just... Okay, so what it's doing is it's taking the sentence, breaking it into tokens, and then essentially just converting every character in the token into an integer, and then just putting all together in an array. And essentially the max length, it just defines it defines the maximum length. Say 20. I'm not so sure I understand max length. Okay. So actually this has got a definitely, this actually is characters. It's not words, it's characters. That recovers the whole, the quick brown fox comes over the la. Okay. Max length. Max length. And now I go. Yeah, that recovers the whole sentence. Okay, so that is actually characters. That's the length of the sentence. Not words, but characters. That's words, but characters, and that's how we recover the whole thing. Cool. That was a good first step. As I said, this is going to be a very slow process, but we're going to understand everything from the bottom to the top. Okay? No libraries included. See you next time.